some wave function or some electron density. So the most typical option is the thing that's called here core Hamiltonian, where you just take the wave function like it would be if you would have non-interacting atoms. So you take just oxygen wave function and hydrogen wave function and hydrogen wave function as a start before you go through these iterations where you always get a better and better wave function.
Can you imagine? So let's look only at one OH. So here I have the O, and somewhere around the O I have the electron density of the electrons of oxygen. So the electrons, they are sitting somewhere here. I don't know where, but there's sort of a cloud. It's like fog, and the fog is very dense in the middle, and then when you go outside, it's less and less dense. So the electron cloud is like sort of a localized fog. And then I do the same for the hydrogen. And the hydrogen doesn't work. Okay, and of course the hydrogen has a smaller cloud. So this is my initial guess, right? Of course, you know that the final result will be different. How will the final result will be different? Quantitatively, no, qualitatively, qualitatively. Can you tell me what do you expect for the final result? How will the electron density be for the final result?
At least the lowest energy for the molecule.
Yeah, you're right. The electron density for the lowest energy, the electron density when the molecule is in its ground state. How will it look?
Maybe in a little bit more exact position.
Do you think they will be more localized, the electrons?
Maybe like more like we know at least more exact position of the electron.
No, the uncertainty remains the same. On the contrary, it becomes bigger. Well, chemists, who is chemist here? Chemist to the front. Chemists, they draw a bond.
ตัวหมอกอะตัวหมอกของมันจะไปทางออกซิเจน
Let's make it red. And the chemists, they draw a line. They say this is a bond. What is a bond in terms of electron density?
If a bond they can share electrons.
Exactly.
So the cloud will look more.
Yes, the cloud will look like a peanut.
Yeah.
The cloud will look like a peanut, and of course, you don't know anymore whether the electron is oxygen electron or hydrogen electron. I mean, electron is electron. And so you will have a cloud. Maybe I can find some third color. Do we have green? No, we don't have green. So you know, at the end, the density will be
ถ้ามันเป็นบอลว่าอิเล็กตรอนอยู่จุดไหนกันได้ระหว่างสองอัน
เพราะมันแชร์
You know, again, lots of electrons here, not so many electrons here, and then a little fewer electrons here. So these atomic orbitals, this is really a first guess, right? But the final result will be different. And the final result will be the electron densities look, for water, it looks sort of like two peanuts. Well, not really, because they merge. So when you have a chemical bond, it means that there is some probability or some density of having electrons between the nuclei, shared electrons. And of course, in inorganic chemistry, you learn these little lines and schemes. It just means this. The electron density goes a little bit away from the nuclei. And for the chemist, you know, it's mostly the valence electrons. I mean, the core electrons, they stay pretty much where they are. And the valence electrons, they start making the bond. Okay? So we can expect something like this when Michael now will show the electron density.
Now we have the program has taken a millisecond or something like that to solve this electronic Schrödinger equation. But it has really done it in the way like we described at the beginning of the lecture. And what can we do with that now? Well, if we look here, we can look at some properties. Yeah, actually, properties can mean anything. It can mean things that come from the calculation, or it can just mean the mass of the molecule, which does not come from the calculation. But let's look at orbitals. Philip suggested we look at the orbitals. And now, actually, we did not define now what are our orbitals. I just mentioned that the program takes the so-called atomic orbitals as a starting point for the wave function. And the molecular orbitals that come out, well, we did not define it, you know it from your chemistry lectures.
I'm not sure. Who can define what is an orbital?
The orbital.
Orbital.
For me, it's
S orbital, P orbital, D orbital.
Yeah, so it's
What is this?
It's a shape of the electron in the. It's the
Is
so like if we have like S, P, D, F.
Yes.
Yes,
And-
and they have like the shape for each one. Like
they have different shapes,
yeah,
yes.
different shape. Yeah.
But I mean, can you see them, or is that something real, the orbitals, or? I mean, I have an electron density, right? I have the psi function. How does the psi function or psi squared then? How does that relate to the orbital?
I think it's from the L in the quantum number.
That's right. So the orbitals are the parts of the. So the wave function is just all orbitals together,
Yeah.
but they have different quantum numbers, and so you can look separately. For instance, you can look separately at the electrons which have quantum number 1,
Yeah.
and they're called s orbitals.
Yeah.
But this is sort of a mathematical trick. I mean, in reality you cannot really measure. It's very difficult to measure this.
Yeah.
I mean, you have an atom, and then you make some measurement and say, you electron, if you have the quantum number 1, please say yes. Of course, nobody will answer. So the orbital decomposition is basically a mathematical trick, but it's very useful for the chemist. And it is a decomposition of the electronic density according to quantum numbers. So in some way, orbitals are like basis functions, because you take the density and you decompose it into something,
Yeah.
okay? But it's very useful, as we shall see here.
So the problem is a little bit that for atoms you have really these exact quantum numbers, S, P, D, and so on. But for the molecule, actually it's not. Since they are not spherically symmetric, you don't have these exact quantum numbers. So it's a little bit more arbitrary, but it is very useful. And how can we look at these orbitals? Well, can I make this picture picture bigger? No, maybe not. Okay. Nevertheless, what what you see here, that's something that's called a term diagram, and it is just showing you the energies of the orbitals. And now here you see a green line very low below all the other lines. What orbital will that be?
Chemically, I mean, which, I mean, so we have said when we do the variation principle, we can compute psi h psi for any function, not just the correct eigenfunction of the Hamiltonian, right? So we can compute these energies for guessed wave functions. And we can also compute the energy. We said the orbital is just a part of the real wave function. And of course, we can also compute the energy separately for these parts, right? So we can take the part of the psi function that has quantum number 1s, and we can compute this 1s part, Hamiltonian 1s, and we get some energy. And this is what is drawn here. And so from your expectation, just from your knowledge of physics or chemistry, which electrons do you think, or the density of which electrons do you think bring the lowest energy to the system? That's a real question for chemists. Which electrons, so the whole system has some energy, and then you decompose the energy and you say, okay, this energy, this comes from the electrons with quantum number 1s, so I call it the 1s orbital energy, and this energy comes from the electron with the quantum number 2px, 2py, 2pz, so I call it the p orbital energy. Which one do you think is low, and which one do you think is not so low? What does the engineering tell these chemists what they don't know?
It's 1s.
Exactly. Of course it's 1s. Very good. Excellent. Yes.
So I did not say some details, for example, that in the water molecule normally all the electrons are paired, so you have 2 electrons in each molecular orbital. And you can already guess the green lines, they are the occupied molecular orbitals. And the violet or whatever color it is, lines, they are the unoccupied ones. And the thing that's a little bit interesting is really that there's such a big difference between the 1s and all of the rest. And that really means the inner shells don't do much for the chemistry. So let's see if we can make a picture of it. And picture is always a little bit also something that needs some explanation. Yeah, I will explain quickly then what I was doing. Okay, so now I have tried to plot the 1s orbital of the oxygen. But what does that actually mean? Because the orbitals are functions in space, and they are just like the wave function, or like the wave function, and they are continuous functions. So how can you plot that? Well, basically, you cannot plot it because at each value in space, you have just one value of your function, and the space is three-dimensional. So what you do is you plot a so-called isosurface. Isosurface means that you tell the program, look where the value of my orbital is 0.01 units per cubic angstrom, and then the program looks all over the space, and everywhere where it finds exactly this value, it makes it green. And that's what I have done. And so, of course, that's completely arbitrary, because if I tell the program instead of 0.01, plot me everywhere where the value of the function is 0.001 units per cubic angstrom. And then with a smaller contour isosurface number, I would get a larger green ball, because hopefully this orbital has the maximal density at the oxygen in the center of the nucleus, and then it gets down and down and down. So that's what the Gauss function is doing. And so it really tells you only the relative shape of the 1s orbital. It's not that the size has no information.
I mean, there's, people always speak about size of atoms or size of this, size of that. So I say, okay, radius of an oxygen atom is, 0.9 angstrom or whatever. And this is totally arbitrary, because the electron density, even the electron density of a single atom, that goes everywhere, right? So here I've tried to plot what Michael was just saying, that you do these isosurfaces, but if I do it only, why do I always pick the one that doesn't work? If I plot only in one dimension, let's say x, and here maybe psi square of x, or maybe this is the psi square only for the s electron, so it's the s orbital. It looks like this. So where is the limit? You don't know. So when you make these graphics, these drawings, you just decide, like Michael said, I will make a limit somewhere. So maybe I have 90% or 95% or some percent inside. So, I will say this atom is so big, maybe 1 angstrom. If here the integral is 95% and only 5% is outside, or 99% or whatever. So this is how people define sizes of atoms, right? Because you can really not use psi or psi square, same thing, because they go to infinity.
Yeah, and with the orbitals it's just the same, but that does not mean that it is useless, because the shape is also, or the shape is very important, and that you can look at. Let's look at the shape of some of the other orbitals. How can I make this a little bit, I think that way, all right. So here we have a few other green orbitals. And let's go here at this one. Oh no, let's go to this one. Let's see how that looks like. And now I set this ISO value to a very large number, or how did I set it? I cannot remember what it was before, but I think it was a smaller number before, and then plot. Yeah, okay.
What?
So that is that's a bonding orbital of the water molecule, I think. And here the program has one orbital that encompasses the two hydrogens. No, it's not a bonding orbital of the water molecule. It's an orbital that belongs just to the hydrogens, because the wave function has different signs on both hydrogens, and so it is 0 at the oxygen. So the red thing is not the orbital, it's just the oxygen atom. And so this orbital has this orbital belongs to the hydrogens alone. And
this is psi square, but the underlying psi, this is positive on one side and negative on the other side.
very often the people look, of course, at the density at the psi square, and you can do that. So if you look at the psi square, it has only one color. Well, that's the positive color for the program. Green means positive, and the violet, the blue one, I don't know what that is negative. And what about the other ones? Well, here, for example, okay, here I have another orbit that belongs only to the oxygen, and that's probably the 2s of the oxygen. I mean, I'm not sure myself, but it looks like. It has no contribution at the hydrogens. And so on.
And if you plot everything together, I don't know whether it's possible, then you should get these peanut-shaped things. And this tells you how to decompose the peanut-shaped things. And, some are plus minus and some are plus or minus minus. And you can just learn things from looking at this.
Let's do that also. And what did I want to say? Well, you see there's a large number of unoccupied orbitals. And these unoccupied orbitals, they are largely meaningless. They are just a byproduct of the eigenvalue calculation. And the higher in energy these orbitals that are unoccupied, well, unoccupied, if they have no electrons, you cannot measure them, of course. So that's why they are largely meaningless. They are getting quite complicated. It's fun to look at them. So for example, that would be some, I don't know, orbital number 30, yeah, it's, so if the energy goes up, there are always more and more node planes where the wave function goes through a zero, and that costs some energy. Each node makes the wave function more and more energetically unfavorable.
I mean, these unoccupied orbitals, of course, they serve as partner when you want to excite the electron. So I don't know. You are sitting, of course, your molecule most of the time, not always, but most of the time, your molecule has only the occupied orbitals, because the electrons want to go to the lowest energy. Okay, and then I don't know which ones, they are all unoccupied. So somewhere down here we have the occupied orbitals, and then we send light, quantum, h nu. And then of course the question is, can I find the correct gap between the occupied orbital and an unoccupied one? And then I will have absorption. So these unoccupied orbitals, they are sort of the partners that can make a proper gap so that you can absorb a quantum. And then you said, I have excited my molecule. So the electron is in the formerly unoccupied, now occupied orbital. But it will not stay there because the energy is so high. So it will go down, exactly. So unoccupied means unoccupied when everything is at its lowest energy. But as we share, I mean, of course, the molecule can absorb a quantum, and other things can happen to the molecule, so that sometimes the occupied orbital is unoccupied and the unoccupied is occupied, but then it goes down again. I'd like to put in the first year chemistry exam, I always put the question, not always, but very often, is it possible for the hydrogen atom to be in a 2s state? And the students always answer, no, hydrogen is 1s. Yeah, true, that's the ground state, but you can excite it, it can go to 2s. So it is quite possible for hydrogen to be in 2s, just not very long, because it would come down again, okay? And so this is why you study these unoccupied orbitals, because they will tell you about the possibilities to interact with the molecule.
Yeah, and Philip has pointed it out already that these orbitals, they are nice, and the people analyze them a lot, and of course they give you nice pictures, and especially when you have some ionization or electron transfer or so. But they are not really so fundamental as the total wave function. And so one can look, of course, also at the total wave function. And if we do that,
I mean, this one advantage of this orbital thinking, which is mathematic, I mean, it's a trick, is that we said yesterday, remember I stressed that this condition, this energy condition, is a necessary condition, not sufficient. And so sometimes, for instance, you can have transition only from one s orbital to another s orbital. Making a transition from S to P, that's already much more difficult. Okay? So looking at these orbitals, and these orbitals, they reflect symmetry, they can help you understand which transitions will really happen. So S2S is better than S2P, and PX, PY I think is totally impossible, and I don't know what, I mean, it's, so you can derive these selection rules from looking at these orbitals.
Yeah, and I was just trying to find a nice ISO value, because we have the same problem. The wave function is a function in three-dimensional space, and I can just pick a value surface. And so if I do that, maybe a little bit a larger number, then one sees nicely this peanut shape. And let's do that. Maybe so. So maybe it's enough now. No, not a good idea.
Still not peanuts enough. You see, if you look from very far away, then the electron density of water bottle is almost a sphere.
Yeah, maybe something like that.
And if you look closer and closer and closer, then suddenly you start seeing the shape.
Let's see. No, it was too much.
Now it's
And you see, it's the size is really arbitrary. You can select what you want, and but now I have had some reasonable size. That was this one, and I'm happy with it. So you can see a little bit this. Then it goes towards the hydrogens.
well, this is a very good representation. You see one thing. You see that the electrons, somehow they like better to go to the oxygen than to go to the hydrogen. Right? So, I mean, this ISO value looked like this, and if I would take a little smaller ISO value, maybe it will look like this, and then another little smaller will look like this. But always you will find that the electrons, they like to go better to the oxygen. And this is something that chemists know very well. Exactly, it has to do with the electronegativity, right? Electronegative atoms are atoms where the electrons don't like to go so much. And no, that's a positive one. The negative ones is where the electrons like to go. So, I mean, there are charges on the nuclei. I mean, of course, the charges on the nuclei, they don't change. And they are compensated by the electronic cloud. Okay? And of course, if you have an atom, then the center of the electronic cloud is exactly the center where the nucleus is. Right? The center of the negative charges and the center of the positive charge is the same. But here it's not the case. Here you see you have more negative charge here because the electrons like to go here. And you have more positive charge, let's say here, because there's not quite enough electrons here to compensate the +1. This is something that is very important when you want to study the interaction of molecules. What is it? How do you call it if the electrons like better to go to one side and not so much to go to the other side?
Polarizability.
It's not the polarizability, but it's related. It's the dipole moment, right? This is why water is a polar molecule. This is why we say water is polar, because it has a dipole moment, right? It's sort of like a little magnet, but it's an electric magnet, if I can say that. So it behaves like a magnetic dipole, but it's electric. So the typical thing of polar liquids, I mean alcohols and water and whatever, is that somewhere in the molecule there is a spot where the electrons like to go and a spot where the electrons don't like so much to go. And that makes a dipole moment.
And now maybe a little bit complicated, but nevertheless something that maybe you have already heard of is if you are a chemist, you have probably heard of nucleophilic and electrophilic reactions or substitutions or whatsoever. And so the water molecule has two sides. It has the side where it attracts nuclei, that's the oxygen side where the negative charge is and it attracts positive charge, and the other side where the hydrogens are. And the chemists, they have a generalization of the dipole moment that they call electrostatic potential. And with this electrostatic potential, they can try to say, aha, my nucleophile will move here and my electrophile moves there, and then maybe they can react with each other. And for that reason, these computer codes can all make pictures also of the electrostatic potential. And it's basically the same as the dipole moment, but it's also a function in space. So I can try to plot that.
Well, let's first maybe think about it. Always good to exercise your imagination. If I take another water molecule, I take a second water molecule, where will it go and how will it sit with respect to the first water molecule? Okay, I will make with my fingers. So let's say this is this water molecule, right? Oxygen and two hydrogens. Then I have another water molecule. Where will it go? Will it go like this? Or will it go like this? Or will it go like this? Or where do you think it will go?
The electron count will be like opposite of each other.
Hmm?
The electron count.
Like this? It will sit like this?
Yep.
No.
No, like this.
No, not like this either.
Like this.
Like this.
Yes, yes. Of course, this is positive, right?
Oh.
This is negative. And of course, the positive we like to go to the negative. So the other water molecule with the hydrogen of the other water molecule will sit here. Or the oxygen of some other water. So, I can have one here where the oxygen goes towards the hydrogen, or maybe one here where the oxygen goes toward the hydrogen. Or in the back where the hydrogen goes toward the oxygen. How is this called, this very particular arrangement in water where a hydrogen points towards an oxygen?
Hydrogen bond.
Exactly, this is the hydrogen bond. This is we can explain very easily the hydrogen bond just by looking at this. It's just that the positive end likes to go to the negative end.
Yeah, and what the people often do is they take just a wave function or some other shape of some other picture of the molecule, and they plot the electrostatic potential on this function, so that you can still see approximately the shape of the molecule and which are then the parts that attract the hydrogens and the parts that attract more the oxygens. And let me do that. Let me make it a little bit bigger here. Okay. Yeah, well. So here the hydrogens are still there, so you can not see this green part. The green part is the part that attracts the oxygens, and I will make it a little bit more visible.
So you see this representation, probably you have studied representation where you write sort of partial charges. And this is just an approximation. You see, in reality it's continuous. But
So it's maybe a little bit
yeah,
better.
right. But the partial charge representation, of course, is very useful because it's much simpler than the continuous function.
On the left side, the green is positive, and the bluish violet thing, that's negative. And that shows you which part of your molecule attracts some other molecule or some functional group. Of course, for the water, you don't need that, you know it. Everybody knows
People in
it.
biology, for instance, if you want to study interaction of drug molecules with membranes, this is one thing you look at. You plot this electrostatic potential surface or whatever you call it for your protein, and this will tell you where the drug molecule can go and where it can dock or cannot dock and all kinds of things like that. So this is something that is very, very much used in the pharmaceutical industry.
So it's really, let's think our cursor here, our cross hatch is a fluorine ion. The fluorine ion moves around and it goes here. Fluorine is negative, I don't go here, I don't want to go here, but here I might be boo boo.
Here is nice because
Here I
the energy
go
is
to make maybe hydrogen fluoride. Yeah, so this is also something that is a perfect physical quantity, this electrostatic potential and the wave function. With the orbitals it's a little bit more difficult, but on the other side they contain much nice information. You must just be careful. And what else do we have for the Schrödinger equation or the wave function can tell us from?
To prepare for tomorrow where we are going to speak about the nuclei, can you do a geometry optimization? I mean, all your programs, Gaussian, there is one button, you click and it says optimize the geometry. What does the program do when you say optimize the geometry? Well, you say it optimizes the geometry, yes, but what does it mean?
Make the arrangement of the atom at the lowest energy as possible.
That's right. It looks for the lowest energy position of the. I mean, the position of the atoms that correspond to the lowest electronic energy. And how does it find it?
Calculation iterations.
Yes, but what does it iterate? Let's say I have a diatomic molecule and I start, again, you do calculations because you don't know things. So I have some diatomic molecule, I don't know the equilibrium distance. I don't know the distance between the two atoms when it is in the ground state. So I do, well, like here, let's say this is my diatomic molecule and I make some guess. So let's say we call it R1 and let's guess. And now I will plot here R1 and the energy. So I can take my Gaussian program, take this geometry, which in the case of diatomic means just distance, because of course the energy does not depend whether your molecule is like this or like this or like this. I mean, we don't count the gravitational field, right? It's just so much smaller. We don't counted. So our energies are really position independent. So we have only one coordinate, and that's the distance. So I set the distance, some, you know, not too stupid value, maybe 1.5 angstrom, and I compute the energy. So let's say 1.5 angstrom, and I get some energy. And of course I get the ground state energy, and then maybe I get some excited state energies, which are not so very important for me. Now, how do I find whether for some other geometry there is a lower energy? Which is the question I want to answer.
I can repeat the question.
The question is, I have selected arbitrarily one geometry, and I can, of course, I can compute the wave function and I can compute the energy using a program like this. But I don't know whether this is the correct distance. But when you click optimize, the program will find the equilibrium distance. And the question is, how does the program find it?
You just compare, and when you got an energy, right? You add E1 and compare to E2.
And how do you get E2?
Use the E1 and optimize, change the angle or something.
That's right. You just change the distance. So I have selected a distance of 1.5, let's say. So now I select a distance of 1.4. Remember, in our calculations, the atoms do not move. So I have to move them myself. So I take 1.5, I nail the atoms to the board, and I make my calculations. Atoms don't move. But of course, I'm free to nail them at some different position and redo the calculation. So I redo the calculation and I find another energy. And this energy maybe is lower, let's say. So the program makes a guess. The program says, well, if making the distance shorter lowers the energy, then let's do the same trick again. And you recompute the energy. Now maybe this time it's higher. So what you conclude, you say the minimum energy must be between 1.3 and 1.5. So now you can redo the whole thing with smaller steps. And you know, when your step is maybe 0.01 angstrom or something like that, you say, okay, good enough. So you determine at the end that your minimum maybe is, I don't know, here something. And then you call this optimum. I mean, optimum means best possible. Of course, it's not best possible. It's a crazy name, but it's you know, people use this term. It is just the lowest possible electronic energy as a function of the positions of the nuclei. And that the programs can do automatically. I mean, this try and error and check whether it goes down and check whether it goes up and make the steps smaller, and this is something you can program and make automatically. You don't have to say do step like this and step like that.
Let's try it. Maybe let's assume our program is not so clever that it knows that water has approximately this geometry. Let's say, okay, maybe the program is a little bit stupid and it has a water bond length of something like this, and let's assume the program is also stupid and the water HOH angle is also different.
You know, water everybody knows, but if you have a new molecule, then, you know, it's not in this database that you use at the beginning. You know, that's a database of good guesses. So You have to guess yourself.
So that would be a water molecule that really needs an optimization. And so we do just the same thing. We say set up, okay, that's we have already there from the last time. And then we compute, but we do not compute a single point, but we compute geometry optimization. And then there are some options because this minimization can be done in different ways, which is just a mathematical method.
I mean, of course, in one dimension, it's very easy. For a real molecule, you know, you have so many distances and so many angles that you have to treat at the same time. So it's more complicated. I mean, in one dimension, but the principle is the same.
Okay, let's see.
You can see how it sort of tries a little bit.
Yeah, now it has already found the correct geometry. And so you just like Philip has said, for calculating the energy, we have some iteration. And for calculating the geometry, we put another level of iterations on top of the Schrödinger equation iterations. So for every cycle or for every new geometry, we must do the Schrödinger iterations. And then we need maybe also 10 or 20 geometry iterations. And so that takes a longer time, of course, than a single point. But it is a very handy and important feature. Yeah, and since we have this program here, yeah, we could also calculate vibrational spectra, because that's actually a little bit similar to the geometry optimization, but it has a very well-defined number of calculations. For the geometry optimization, you don't know when you will be finished. You will only be finished when the energy doesn't change anymore. But if you want to calculate a vibrational force constant, you know you must just go a little bit to the left of the equilibrium and a little bit of the to the right of the equilibrium, and then you know the energy change and you can calculate the force constant. So that is something that is also very, very often done.
If it can do the blue thing, it can also find this red curve. And of course this red curve, you say, is some constant times, now let's call this, which it has found here, let's call this x equilibrium. So this would be k times x minus x equilibrium squared. And of course the program can find this. I mean, basically it finds it by computing the second derivative at the minimum. And so basically it says, okay, this looks like Hooke's law, right? And then I can use this other Hamiltonian that we have written down for Hooke's law or harmonic motions and compute the vibrations. So this optimization business and getting the force constants and getting the harmonic potentials and using that for computing vibrations, this is really the same thing. Right? If you can do one, you can easily do the other.
Yeah, but we will speak anyhow about vibrations of molecules in detail. And well, maybe that were really the most interesting things from the wave function. And yeah, maybe just one remark. We have looked at these isosurfaces. Water is a planar molecule, so one can also calculate, one can also look at the orbitals or at the wave function in terms of a two-dimensional visualization or two-dimensional picture. One can just look at it in such a way. But that's only because water is a planar molecule. No, normally that is not possible.
For 3D, for real 3D molecules, you cannot do that. So you need molecules which have symmetry planes. This is just another representation. Okay, so tomorrow we will start with a picture, with a graph like this, that we know how to compute the electronic energies for different positions of the nuclei, for different geometries, and we will take advantage of that. So tomorrow we start with this. And this will tell us, who asked the question yesterday, we know how to study the electrons, but how do we study the motion of the nuclei? Well, you see, one part of the answer is already here. I mean, if the motion of the nuclei is just vibration, then you can do it by just fitting these harmonic potentials. But harmonic motions, in some sense, are not very interesting, because, for instance, they do not allow for diffusion. You cannot have diffusion. Well, you know very often the diffusion, I mean, even if the system is at equilibrium, the molecules don't stay put, they move. Like Brownian motion, right? So if you describe your molecules with things like that, they cannot make Brownian motion. So we have to be better than this. We have to use a better approximation. And this is what we will do. Well, this is what we will do tomorrow and what we will do all the time next spring. The buckyball.
Yeah. Yeah, I have shown you this example today with the HyperCam program, and you will maybe in your work with your thesis more often use the Gaussian program. I have used HyperCam because it's more interactive, but you can do exactly the same things with the Gaussian program. And so I could now show you an example with the water molecule and so on, but it takes a little bit more time. So I will not. I only say it's really the same thing.
I have a question. You say that this graph is like a harmonic potentials because
Well, I just, because for vibrations, if we have really vibrations, we need only harmonic potentials. But of course, and this is what we will do tomorrow, from very similar thinking, I can get also not harmonic, so other types of potential. This is not restricted, this argument is not restricted to harmonic potentials. So, do you know about Lennard-Jones potentials or things? No? So, tomorrow.
because
yeah.
we vary the length of the bonding.
Yes.
So we have the vary of the length of the bonding is like the vibration, so it can represent the reference.
That's right. In some cases, I mean, typically, if the interaction is strong, which means this energy here is very low, then I mean the harmonic potential is just a fit. It's a representation. It's not the reality. I mean, your real molecule does not have a spring. So, but very, very often using this spring potential is a good approximation. And of course you have to study how good or how bad, and this is something that you can do with spectroscopy, because from these harmonic potential you can compute all the molecular vibrations, and then you can compare with infrared or compare with the Raman, and it tells you whether you understood things correctly, and you can use it to identify your molecules and all kinds of things like that. No, you look puzzled. So the general answer is this is a completely general procedure. It's not restricted to harmonic. Harmonic is just the simplest case.
Is have a difference. Another besides form the harmonic potential, right?
Well, let's talk about physics. They don't have cleaner anymore.
No.
Used to supply cleaner, but there is nothing.
เราจะบอกว่ามันมี harmonic potential มันแค่เป็นอีก approximation แต่มันไม่จำเป็นต้องเป็น harmonic potential มันเป็นอีกแบบนึงใช่ไหม
สมอง
Magst
ฟิ
du
ว
da den,
Oder schieb das einfach weg dann mal.
ถ้าเราจะสงสัยว่า
das
แบบ
kannst du ja hier schreiben.
Oder ich schreib da vorne.
เขาแค่จะถามว่าอันที่เราแบบว่าเปลี่ยนบอล
So
ใช่ไหมมันก็เหมือนกับ vibration อะ
why is the harmonic potential sometimes not very
ที่
good?
มันเปลี่ยนไปเรื่อยๆแล้ว harmonic potential มันก็แค่เป็น approximation หนึ่งที่ตรง
Why is the harmonic potential sometimes not very good? So I take again.
รู้โมเลกุลได้จากอีกอย่างหนึ่งที่
That move?
ใช่ เหมือน harmonic potential มันแค่เป็นอีก approximation หนึ่งในการ curve ของ energy แต่มันก็จะมี curve ของ energy ที่
Ja.
อีกเม็ดออกมันดีกว่าซึ่งอาจารย์พูดชื่อมีคนจำไม่ได้อะ บาง
technician
ที
boy
มัน harmonic potential มันก็อาจจะดีในกรณีนี้
So why is the harmonic potential not very good?
โอเค
So I take again some diatomic molecule, maybe HCl. And maybe I have optimized the distance. So I know the minimum energy of this is for, I don't know what is the OCl distance, 1 point something angstrom. I don't know. So let's call this R minimum. So if I plot here R, and here I have R minimum, then I know this has the lowest energy. Okay? Now, what do you expect will happen if I push the two together? If I make the distance smaller, what will happen? The energy will just increase. So probably the energy will go something like this, very, very steeply, because of course you cannot put the two atoms one on top of the other. What will happen if I pull?
energy is gonna be lower
The energy will go lower, even lower and lower and lower?
No.
No? What will it do? So I pull and pull and pull, and it never breaks. But if I pull very, very hard, the molecule will dissociate, the bond will break.
Yeah.
I can break the bond. So how does the potential look like that describes bond breaking?
is learning go to zero.
It goes to zero. Because if the two atoms are very, very far apart, then the energy does not change when I move, so the potential is zero. So the real potential for this thing, it will look like this.
Now, of course, the harmonic potential, can I change the color somehow? Yes. The harmonic potential, the harmonic potential, it looks something like this. Right, it goes just like x squared. Right, so this is some constant, which is called the force constant, times, well, I call it R, so let's call it R minus R equilibrium squared. So you see, if the molecule is very stable, if this energy is low here, and the molecule does not dissociate normally, then the harmonic potential is a reasonable, is a good approximation. But if you want, or if you know this energy here is not very low, and by not very low, I mean not very low compared to thermal energy, to kT, then my molecule eventually will dissociate. And of course, then the harmonic approximation is just terrible. So again, we have to compare to kT. You know, some molecules never dissociate, but some molecules do dissociate. For instance, water. How do you know that water molecule dissociates in liquid water? Or does it? Or doesn't it? We're talking about dissociation, right?
Yes.
And we talked about the water molecule. And we said water molecule in water, so in liquid water.
Oh.
And the question is, does water molecule in liquid water always stay together? So always the same O with the same H, or sometimes some H goes away and the molecule dissociates?
I thought is bonding each other away.
Okay, and this bonding to each other, this hydrogen bond, I mean, come on. You.
My gosh.
You're a water molecule. Okay? You're a water molecule, this is oxygen, this is hydrogen. And on the other side is something. Now I'm some other water molecule and I make a hydrogen bond with you. And I pull. What will happen? It will dissociate. I will pull away the hydrogen. And how is this called? This is something you know.
I forgot that.
If water molecule dissociates in liquid water, it makes H plus, so the thing that comes out, and OH minus. And what is this called? What is this? You can measure this in the lab. It's very, very important in chemistry. The pH. Right, the pH is the percentage of OH plus in your solution. But it's very, very, very small. You know, 1 in every, I don't know, well, pH 7, 10 to the minus 7. So 1 in every 10 to the 7th molecule is dissociated. So 6,999,999 molecules are not dissociated, but 1 is. So water, you can probably use the harmonic potential because this percentage of dissociated molecules is so small. But other liquids, many dissociated molecules. And so there the harmonic description is very bad. So the correct potentials, they always look like this, because somehow there is always some way to destroy the molecule. So the fact that at some big distance the energy becomes 0, or you set 0, it's arbitrary, you know, where you set the 0 is arbitrary. So you decide when the two atoms are far away, the energy will be 0. That represents the fact that molecules are not really stable. I mean, sometimes some molecules, they stay together for a very, very long time, and some not. But in general, the lifetime of a molecule is not infinite. But that we will discuss tomorrow. This is already anticipating on what we will discuss tomorrow. Tomorrow, 9 o'clock or 1 o'clock? I forgot again. Friday was 1 o'clock.
Is it Friday?
Tomorrow's 9 o'clock.
Friday.
Oh, Friday เหรอ
Friday's okay?
Friday,
You
yeah.
stay Friday?
Yeah.
So tomorrow, 1 o'clock like today.
Yeah.
Yeah.
พรุ่งนี้วันจันทร์เอ้ย
พรุ่งนี้วันพฤหัส
What?
We say that tomorrow is one day or some, for some reason.
Questions?
Just to make sure
Yeah.
that if it has a count of the dissociation of the molecule, the harmonic is terrible, right?
Yes.
Okay.
Because you know, harmonic would mean you need infinitely high energy. You know, it goes to infinity here, up and up and up and up. It never turns around. It goes to infinity, and nobody has infinite energy.
I'm sorry.
พอแล้วค่ะพอแล้ววันนี้เบนตี้เดี๋ยวเบนกินกาแฟอ่ะขอโทษนะทุกคน
กาแฟไม่อยู่เดือนอยู่
กินกาแฟ